Hey everyone, in the last video we were discussing the solution for the burst balloon problem and we solved it using the naive recursion method. And the time complexity for for that problem using the solution of naive recursion was n multiplied by 2 raised to the power n, which is not good. So in this video we will take a look at a dynamic programming solution for the same problem and see how dynamic programming improves the complexity for the solution. Okay. So in the last video, if you remember, the input was 3158 and we added a 1 at the end and a 1 at the beginning. So now let's quickly just go over the problem statement once again. And the problem statement says that given an array of balloons, we can pop any given balloon, and when we pop, the points we will get is the multiplication of these three numbers. Basically, the numbers which are adjacent to the current balloon and the current number. And we have to maximize the points. So this was the problem. And in the previous video, we discussed a solution for the naive recursion method. So let's see like how dynamic programming can improve the complexity of the problem. Now, before jumping into dynamic programming, let's see is there any other way to break down this problem? Because last in the last video, if you see that the time complexity for this problem was n multiplied by 2 raised to the power n. So this means that for every element we are having 2 raised to the power n states in the problem in the solution. Now what we want to do is this, since this is a very expensive time complexity, we want to reduce the complexity of this part. Now if you see, like when we were in the last method, we were picking one balloon, and for the remaining balloon we were calling the subproblem balloons, we were calling the subproblem recursively. Now what this did was this broke down the problem from n by 1. So by 1, if you reduce the problem, you get a new problem size of n minus 1 plus whatever you are getting the solution for the current one. Let's call it k, and we were doing it n times. Okay, so this is what we were trying to do using the naive recursion method. Now let's see, is there another way to break down this problem so that we again get the same category of problem. Okay, so now let's take the example this 1 3 1 5 8 and 1. Now remember that our original input is from here to here, only this part. We have added two other ones just to simplify the problem, because if you pop the balloon at the end point, there is no other balloon on the right side, so that why we added this uh, sentinel balloon. Okay, now if you see that if we pick any balloon, let's say we pick 5. Okay, so if we pick 5 and burst it, so now what is happening to the array? So if you see, like if 5 is not there, right, let's try to delete 5. So if you see, the array gets broken down into two subarrays. Now this is 1 3 1. This is one part of the subarray, and the other part becomes 8 and 1. So just by busting the balloon, if you see, we have broken down the problem into two smaller versions of the same problem. Like now, what we want to do here is we want to maximize this part of the array, and we have to maximize this part of the array. Now, if we are able to do that, then we have the solution using the divide and conquer method. Now, on thinking this problem in a slight more detail, you will realize that you were able to successfully do the divide part for this problem. But what about the conquer part? How are you going to aggregate the results after the recursive calls come back? So let's discuss the conquer part. So there is one property in the divide and conquer solution It is that if you see like any divide and conquer algorithm, be it merge sort, be it quick sort, or any other standard divide and conquer algorithm. So the basic property to apply divide and conquer is that the sub problems should be independent of each other. Now let's see if the sub problems are independent of each other or not. Now, if you check here, like the next balloon, if you uh, burst, let's say we are going in the left subtree of this recursive solution, and now we are picking this balloon for the next burst. So, what should be the ideal scenario here? Now, the ideal scenario should be that when you are busting five, let's say, let's consider this case, when you are busting five, the ideal scenario should be it should multiply the left hand side and the right hand side. Okay, so here we have the left hand side and this is the middle one. For the right hand side, we have 5. But if you see, what we did is we bursted 5 in the previous step. So we have already busted 5 here. So now we cannot bust 5 here because according to the new state of the array, 5 is not here. Only since we have already destroyed 5, we only have 3, 1 and 8, 1. And now we want to bust 1. And we have subrecursively called this. So now if you see here that uh, so one needs a balloon from the right hand side of this recursive subtree. Now if you see that this problem, this subproblem, right? This subproblem requires an value from the solution on the right subtree. So that if you see that this problem and this problem, in this way, if you divide, these are not interdependent from each other. So what that means is we cannot apply divide and conquer solution on this problem. So now we have to think of another way to solve this problem. Okay, let's try to look at the dynamic programming solution for this problem now. And before discussing that, what we have to do is we have to solve this dependency problem between the subarrays first. So if you, as I have already told that the left subarray or the left recursive part of the problem is depending on the right recursive part. And usually the best way to solve this kind of dependency problem between the subproblems is that depend on the parent instead of depending on the right half or the other half. So here, how can we depend on the parent? Because we are already busting the parent. So so the usual way to solve this problem will be that we need to assume that when we are solving the problem, we are not bursting 5 at once. We are marking it that what will happen if 5 is busted at the end within this range. So for this range, let's say we have left and we have right. What happens when a given element x is busted at the end? So now if you see that there are 4 elements in this array, and in DP solutions or in recursive solutions, we don't know actually which option will yield to the most optimal result. And if you see that in the first iteration itself of the problem, we have 4 possibilities, which is 3, 1, 5, or 8. So we can pick any number with equal probability, and we don't know which one is going to yield the best result. So what we are going to do here is pick all of them one by one. And at the same time, if we see a repeated subarray, which we have already solved in this problem, we are going to use the solution for that subarray from our cache, which will be the memo for the dynamic programming solution. Now, uh, moving forward on this solution, let's take an example that in this 3, 1, 5, and 8, 5 is the last element to be removed from this array of balloons. So now what will happen to the subproblems? We will be creating two subproblems. One will be 3 and 1. So this will be one problem and one will be 8. Okay. So we have marked 5 that we will be busting this a balloon later, which means we will be calculating the result uh, for this fifth element at the end. So now just imagine one thing. If 5 is the last balloon which is to be bursted in this in this array, so at the end only 5 will be remaining, right? And to be able to calculate the points for 5, what was the rule? That we have to, for any given balloon, we have to calculate the points by multiplying the balloon on the left hand side and multiplying the balloon on the right hand side. Now, given that all these balloons have been busted, let's say 3 is busted, 1 is busted, and 8 is busted. So now for 5, which are the two balloons that are on the left hand side or on the right hand side? So it's not 1 and 8. It's this one and it's this one. So let's say we were trying to solve this problem for this range where this is left and this is right. So now if you see that for the fifth, for the 5 element, what are we trying to multiply it? So points is equal to, let's call this array B for balloon. So balloon, for if we want to calculate the points for given element at I, points at I, so this becomes balloons of left minus 1 multiplied by balloon of I multiplied by balloon of right plus 1. So this is how we are going to calculate the points for the number which will be bursting at the end. So let's say for 5, if this problem and this problem is solved, then this is how we are going to calculate the points for 5. So let's say for 5, the L was 1 and the R was 4. Okay. So for 5, what will be the solution? It will be B of 0 multiplied by B of I. So B of 5 will be 5 and multiplied by B of R plus 1, which is B of 5. So B of 5. So now it is 1 into 5 because B of 0 is 1, B of 5 is 1, and B of, which is, what is this index 0, 1, 2, 3? B of 3 is 5. So this will be 5. Okay. So this is one part of the problem where we are calculating the points. How do we add the solution for subarrays? So we looked at the first part of the problem. This is part one. Now let's look at the second part of the problem. What is the second part? How do we add the or how do we consider the solution which is coming from the left hand side and the right hand side? Now, if you look at the problem statement or our function signature, what does that mean? If I call the function for a left element and a right element in this range, this will give me the maximum points I can get by bursting the balloon in the range left and right. So this is essentially giving me the maximum points which I gain if I go in the left side. And since here, if you see, we are going on the both directions. We are going on the left side and we are going on the right side. So now, if all the balloons are already bursted on the left hand side and on the right hand side, what do we need to do? We need to add. We need to add the points we are getting from the left hand side of the problem and from the right hand side of the problem. Okay, so if we take all the conditions into account to create an equation to solve this function, what would that be? So we have two elements in the solution. The first one is points, which we will get after bursting the balloon. And then the second part is the solution from left subtree and the right subtree. And third part is we don't know which of this balloon is going to yield the maximum result. So we have to add the result for all them or check it for all the trees. So if we are trying to find the solution in the range L and R, we have to iterate from L and R by marking every balloon once. So let's say that the iteration uh, element which we will use is I. So now if we want to define this problem, what is the uh, what is the equation? So to even simplify that further, or so that you are able to write the equation yourself, let me consider this example: 3 1 5 8, and let's give the values to every thing in this array. So we are trying to solve this for this L and this R, and let's say our I is at 5. Okay, and we want to solve. So if we want to solve for, let's say, L and R, what are the things we need to consider? We are calling this subproblem for the left half, which is 3 and 1. So if you try to see what is the L and R value for the left half, so this is the L remains same, but the R becomes, what is this? This is I minus 1. Okay. So this problem has a subproblem of f of L and I minus 1. Okay, what is the second part? Second part is just the right half. So if you consider what is the L and R value for this one, so for this one, the L and R value are, if you see this is I, then this is I plus 1. So I plus 1. This is I plus 1, and the R value remains the same. So R. Okay. So now we have the uh, two subproblems. So this condition is checked. Now we need to also include the balloon which is bursted at the end. So we have defined it by points, and let's say points is a function, and if I give it the ith element, it calculates this value. So instead of let me write it like points for now, and I will expand it later. So points of I, and points is a function. We will define this. Okay, so this part is also done. How is part 1 and 2 related with each other? So if we have already found the maximum points we get from this part, and we find the maximum points from this part, all we have to do is calculate the points for this one and add them. So if we add this part with this part, right? So we will get the solution for L and R range, which where I is equal to 5. Basically, I points to 5, element 5. Now, if you see, we discussed also that in BP or recursive problems, we don't know which element will yield the maximum result. So we just don't solve for only one element. We can solve for all the elements. So which means we have to, if we are looking for the solution for range R, L and R, we have to solve starting from L and considering the current element will be busted last till R. So how do we do that? We can do that by considering that I goes from L to R. Now what is the function which we want to compute on every iteration of I? It's the max function. So we will say max function of this term. Now to break this down even further, how did we define points? Let me write it here so that it's very clear. So points of points of I will be calculated as whatever was the L value. So B of L minus 1 multiplied by B of I multiplied by B of R plus 1. So this is how we will be calculating points. So if you want to solve this problem using dynamic programming, this is going to be the recursive structure of your problem. Okay. Now, uh, this is only the recursion part. We have not included dynamic programming yet. So for dynamic programming, how do we cache the results? So if you see in the original problem, how many variable states are there? So there are only two variable states. Okay. So that's why you need a cache which has dimension 2, which means uh, if you create a matrix of dimension equal to 2, which means a two-dimensional matrix, you will be able to store the results for both L and R range. This way, you will be able to, like, let's say any at any point in time, if you see that the sub problem is already solved, which means that you have already found a solution for a given L and R. Instead of calling the recursive function again with so many functions, what you can do is you can just refer to this memo in your table, and this will give you the result. Now, this lookup will save some time, and hence the solution will become a dynamic programming solution instead of a pure recursive solution. Let's also try to see the time complexity of this DB solution. And if you remember, the time complexity for the naive recursion solution was n into 2 power n. So that was the time complexity for the naive recursion solution. And in this solution, what we tried to do is we tried to reduce the number of states caused by this part of the problem in the previous solution. And if you see that we have reduced this from 2 to the power n to n square. Now, how is it n square? Let me tell you. So the total time complexity will be so time complexity will be, so if you see here, we are iterating in the range L to R. So for the biggest range, it will be the size of the array. So we have N. And then if you look at this part of the solution, right? So here we are trying to calculate the solution for all the subarrays in the left half and all the subarrays in the right half. And if you see, like, how many subarrays are there for a given subarray of size n, so that will be n square, or in the complexity of n square. So now if we are, for every element, if we are breaking the array into into all possible subarrays without that element, so we are trying to calculate the solution for the remaining subarrays. So the total time complexity for this solution will be n cube. Okay. If we want to talk about the space complexity for this problem, if you remember, we have a dimensionality of 2 for this problem. So that's why we need a two-dimensional matrix to store the results for this problem. And if the problem size is n, then the number of elements in the matrix will be n square. So that's why the space complexity will be n square. So now we are going to implement this solution for the top-down uh, DP and the bottom-up DP as well. So let's first start with the top-down DP. And before that, let me just write this. Let me just write this in the VS Code. So what we are essentially looking for is that we are looking for max of the things. And so, okay, so for range in L and R, what we are looking for is we pick a I. So let me write that we pick an I. And what does the equation say? So, okay, for the range in L and R, we pick I, where I goes from, okay, so where I goes from L and L to R, causing the other sub problems, and we are having so let's say function of L and R. This gives rise to function of L comma I minus 1 plus the solution of function of I plus 1 comma R and the points from the balloons array. Okay, so this is the top down solution. So let's quickly create the class for the solution. So let's call it solution, and let's create a main method to initialize the input, whatever input we took here. So this is 3158. So let's take 3158. So let's call this balloons, and this is a new array. So let's call this 3, 1, 5, and 8. And if you remember the solution from the previous video, if we solve this problem correctly, it should be 167. So let's see if we can achieve 167 from the solution we discussed. And okay, so let's me create a solution object, and it will call solution.solve with the balloons array. This will return a result, and finally we will print the result. Okay, so now let's define the solve method. So we have the return type as int, so int, and the solve method is taking the input balloons, which is an array, so balloons. Now here if you see, we discussed the that we want to add two more ones on the left part and on the right part of the array. So for that, let's create a new balloons array, and the size for the new balloons array would be two more than the existing balloons. So let's say int n is balloons dot size. Okay, balloons dot length plus 2. Now let's initialize the new balloons array. Okay, now we have to copy the existing balloons array into this uh, new balloons array. So for that, I am going to use a utility method, which is system.arrayCopy, and here the source arrow will be balloons, the source position, which will be 0, the destination array will be new balloons array, so let me pick that, and the destination position will be 1, and the length of the array. Okay, basically this is like up to what length we want to copy the array, so this will be balloons.length. All right, so now we have copied this array into a new array, and we also want to set the sentinel elements as 1. So let's pick the first and last elements of the array as new array as 1. Okay, so now we have new balloons array of 0 set as 1, and new balloons array of n minus 1 is also set as 1. Okay, now let's solve for the top down part, which is let's call it solve recursively, and this will be requiring the input, let's call it balloons only, and we also want a left part and we also want a right part. So this is this L and R, and on top of that, since this is a DP solution, so we will also take a result cache. So few basic conditions first, like if the left becomes greater than right, which means we have crossed the subarray range. So for this, we will return just 0. If we already have a result in the cache, so which means result of cache is not a 0, so we will return result cache of left and right. And this indexing we also need it here. Okay. Now, this is the main part of the solution where we said that for range in L and R, we pick I. So let's create that range. So for int I in left and I is less than right. So this is the range where we want to calculate the solution. So how many options do we have? We have the solution from the left part. So int solution from left part. This will be the same function which is called recursively with balloons left, and here this is I minus 1 and the same result cache. We have a solution from the right part as well. So for that we will have solve recursively again, balloons, and this is I plus 1 right and result cache. Okay, now we want to calculate the points from current balloon. So points from current balloon. Now this will be balloons of left minus 1. If you remember this equation, we said balloons of left minus 1 into balloons of I into balloons of right plus 1. So that is the exact same thing which we are doing. Balloons of left plus 1, balloons of I multiplied by balloons of right plus 1. Okay. Now for the final thing, we have to take a max. So let's put this result in the result cache first. So left and right. Okay, so for the final part we are taking the max as described here and here. So let's take a max. So we want to take a max for the previous value. So result cache of left and right, and the solution from left part plus the solution from right part plus the points from the current balloon. Now once we have this, at the end what we are going to do is return the result cache of left and right, which means we are returning the result for the given range for which this subproblem was called. Now let's call this solve recursive method. So solve recursive. Now here we want to pass the new balloons array. So let's change that new balloons array. Now the left and right, if you remember, we are solving for, so this is the new balloons array and we are solving for this up to here and up to here. So this will be, if this is 0, then this index is 1 and this index is, this is n minus 1 and this is n minus 2. So for this will be 1 and this will be new balloons. Okay, we already have n minus 2 and the result cache. Okay, the result cache we have not declared yet, so let's declare the result cache also. So result cache is new int, and this will be of size n and n, and we want to also return the result. So if you see, we are creating this result cache for size n and n, and if you see, the result will be stored at what index? So we are starting from 1 and we are ending at n minus 2. So the result will be stored at 1 comma n minus 2. So what we need to return is result cache of 1 comma n minus 2. So now if we run this, the solution should be 167. And now you see that the solution is 167, which means we have successfully solved this problem using the top-down solution. Okay. Okay, now we have seen the top-down version of the DP solution. Let's see how can we convert our this solution which we have written for the top-down approach into a bottom-up solution. So whenever you want to convert a top-down solution to a bottom-up solution, I would recommend you to always first print the cache. So let's try to print the cache and see how the DP matrix looks like. So let's quickly print that. Print matrix, and we are here getting a matrix, and for what we are essentially doing here is uh, print every row and column. So we are, for every row, for every column, we are getting that element and matrix of ij. Okay, so this is how we are going to print the matrix, which in our case is the result cats. And we are going to observe how the matrix was filled using this equation and whatever the explanation we had from this discussion. Okay, so let's again run this program. And if you see, this is how the matrix looks like. Okay, now let's have a look at the equation and try to understand that which columns were filled before this one, right? So this is we are calling the solution for n is left is 1 and right is n minus 2. So this is our 1 and n minus 2. So if we look at the equation here, this says we have the sub problem which goes from the same left. So if we consider the rows of the matrix which represents the left side and the columns of the matrix which represent the right side of the array, so this says we are on the same left, but the right has gone uh, to I minus 1. So let's say whatever the I is, right? So we are picking I minus 1. So I minus 1 will be on the this hand side. So basically we are in the same row but in a different column which is before the current column. That's what I minus 1 means, right? So for this we are depending on the solution of the elements which are on the left hand side. Okay, that's part 1. Part 2 is we are also depending on the same column but on the other rows. So which says I plus 1, which means the rows which are below this one. So in the same column, which means the right is fixed, and we are looking at the I plus 1, which means the left has been ported from its original value to the one on the right side of the current I, and that would be the rows which are below the current element in the matrix. So, which means that if I am at a given, let's say we are at a given I and j, so we want the solution to be solved for these numbers which are before this I and j on the left hand side, and the exact like on the bottom, like whatever the numbers are at the bottom, the indexes are at the bottom, like this and this. For this, we want the solution for these indexes and these indexes like 135 and 40, and all these should be available if we want to calculate the result for at this index. Okay, so now it means that if I want to calculate the solution for I and j, I have to fill the elements which are on left hand side and which are on exact downward side of the matrix. So now for this, there are only two ways to fill this. Like if you see that left half of the matrix is 0. Now if we start to fill the matrix diagonally, right? That we fill these diagonals first. Then we go and fill this diagonal. Then we again go and fill this diagonal and this. So if we fill it on a diagonal wise, then we have the result of all the elements for the current index which are on the left hand side, and also for all the elements which are on the exact below or the bottom of the current index. So let's see with an example. So for 159, if we fill diagonally, so we will have filled 3, 15, 40, 40 and 0, and we will also have filled 30, 135, 48 and 0. And then we come here. So we have already filled all the elements on the left side and all the elements at the bottom of this index. Now let's see how can we convert a given top-down solution. Now we know uh, that this is the top-down solution, and we also know which elements we have to fill first. So there are, as I told you, there are only two ways to fill this matrix. Either you can fill it diagonally, or you can start filling from the bottom. So like you fill the bottom of the matrix first, then the row above that, then the row above that, and then the row above that. So basically you will fill the bottom, then you will come on the upper row, and then you will start filling like this. Like you go from left to right, then you come on the upper row, and then you again go from left to right. Similarly, or you have the diagonal way. So in this solution, I will show you how you can convert this solution, and we are going to fill this matrix diagonally. So this is our top-down solution, and let's create a copy of this solution first. So we are going to convert the same solution into a bottom-up solution. So let's put it here, and let's, instead of solving recursively, let's name it solve via uh, bottom-up DP. Okay. Now, since we are solving it via bottom-up DP, we don't need to return anything. So either you can keep void or you can just return the result at the end, but we already have the logic to return the result here. Let me close this terminal so you have a better view. Okay, so now we don't need to return anything. We have put the return type as void, and all these extra corner scenarios are also not required. So let's remove these as well. Okay, so left and right, since we are not calling it recursively, even these parameters are not required. So we will be removing this shortly. And the result cache is okay, we can keep it. So the first part to convert any top-down solution into a bottom-up solution is to replace the recursive calls with the lookups in the matrix. So instead of recursively calling for left and I minus 1, we will assume that it was already solved for the problems and the result is already there in the result cache. So we basically just, instead of calling this subproblem recursively, we will just look into the result cache for this problem. So let's just look into the result cache for this problem by this lookup. So here by this lookup, we mean that we are just looking for the solution in the result cache. Let's do the same thing for this next call also. Okay, so now instead of calling the subproblems recursively, we are just looking into the result cache and everything else remains same. Now, how do we simulate what was already happening? So if you remember the analysis from the DP table, which was here, we are trying to fill the matrix in a bottom-up manner and in a diagonal basis. So for filling the matrix in a diagonal basis, if you see, this is for 1 1, this is for 2 2, this is for 3 3, this is for 4 4. If you come into this diagonal, this index is 1 2, this index is 2 3, this index is 3 4, which means every time on every iteration we are increasing the size of subarray by 1. Okay, so let's keep this solution as it is, and let's try to add the extra iteration. So let's see, like, let's keep n equal to whatever balloons dot length is, so we don't have to query it all the time, and we are filling it diagonally. So, and starting for from array of gap 1 or size 1, subarray of size 1. So let's call it gap equal to 1, and we want to go from gap equal to 1 to gap of n minus 2. If you remember in the original problem, this is, we have added two ones and we want to go till n minus 2 because array index starts with 0, so this is n minus 1 and this is n minus 2. So we want to go from gap of 1 to gap of n minus 2. Okay, so we have already set up a gap here. Okay, now what? Now we know what is the gap value. We want to calculate the left hand side and the right hand side of the gap. So to calculate the left hand side and right hand side, okay, so now we want to calculate the bounds for the left and right. So how are we going to do that? So since we know that the gap is value 1, now we say that the left starts at the leftmost side every time we are iterating. So you know that, right? If you look at this matrix, you know every time in every iteration you are starting at this first row. So left goes from 1. Okay, you have filled it diagonally, then you again come to this row and left is again 1. You fill diagonally, you again come to this row, so left is 1. So that's why I have kept left is equal to 1. Okay, now till how far we are gonna go. So this is the maximum value for left. So if we want to reference this element using the gap property, how can we do that? So if you see the next element, this index is n minus 1. Okay, and right now if you see the value of gap is 1. So if we can decrement one more in n minus 1, we can reach this position. Okay, so now let's try to take left is less than or equal to n minus 1 minus the gap. And now since on every iteration we want to increase the value of left, that's why we will be increasing left by 1. Now we also have to calculate the right hand side of the array. So for that, let's take right, and the value of right should be whatever the value of left is there plus the gap between the left and right. And just for the sake, since the array is 0 indexed, we take left plus gap minus 1. Now if you see, we have both the bounds. We have the left bound and we have the right bound. And since we have already calculated left and right, we don't need these two anymore. So we are going to remove that and just keep this. So now if you see, we have successfully converted our solution to bottom up DP, where we are filling the matrix for the smaller versions of the problem and then making a bigger solution out of that. So now let me show you that if I call, instead of solving recursively, if I call the bottom up version of the same problem, this is going to still give me the same result. So where is this? This is solved by bottom up DP, and we don't need this left and right. And let's run this. So now you see when we ran for the from the bottom up solution as well, we are getting the same solution. So that's how you convert a top down solution to a bottom up solution. You basically copy it, you get rid of the sub recursive calls and convert it to the lookup calls in the cache, and then whatever you were recursing on the range, you basically try to generate that same range using iteration and just copy this part of the solution inside your iteration once you have uh, got the left and right bounds of that of your solution. So that's how we basically convert the top-down recursion to a bottom-up top-down DP solution to a bottom-up DP solution. And this is how you should also structure your code in an interview perspective, and this is how you should explain it. Like every single line, point by point, giving explanations to whatever the solutions you have drawn on the whiteboard, and that's how you should go about it. Okay.